Thank you.
I hope it's okay if we interrupt along the way.
Sorry.
I hope it's okay if we interrupt.
Yeah, please do.
Great.
Yeah. And please do interrupt me if I say something gibberish. Okay. So let's start with the and we will first state the main results. And then we will build up to them. So page first. Build modules. So we'll then define KKB and state the functoriality. Then the technical part. It is called the technical theorem. And finally, the Kasparov product and its properties. So this will be all the results will be stated in a single theorem, which would be called perhaps the applicable KK. But if you want to compute KK of some guys, so like A and B, then we will actually need the constructions from here and here. So that is, but to do this stuff, I have to go through all these things. So therefore, these two are the preliminaries for these two. And so the number 2 point is to compute with them. But if you want to apply, it suffices to take the main big theorem. Okay. Here we go. Whoops. You still have a big screen.
Might be very disturbing for
the camera upside down. That's true.
I thought you were going to say move the camera.
No, I was referring to the
I see.
reflection problem.
Yes, the writing is just
Yeah.
visibility.
Sorry, I totally didn't do
It's not.
Okay, no, that's good. That's cameras.
that. Sorry, I'm getting the roll. There we go.
Like, it's really good.
Yeah.
I is the cylinder of A. That's the continuous functions of from the interval unit interval 0, 1 to the system A. If you take A to be C of X or C0 of X for some locally compact Hausdorff space, you see the cylinder X cross I. And C of X cross I by some exponential law is C of I tensor C of X, and you replace the C of X by A here. So IA comes equipped with subjections for each T in the unit interval. Phi T takes xi and gives you xi T. So these are called T. Definition. Suppose we have to start homomorphisms. Two more questions. F is homotopic to G if there exists a star homomorphism, so I just have star homo from which is H to the cylinder of B. Such that we go through H first and then apply evaluation at 0, pi 0, you get F. You go through H again and apply evaluation at 1, you get G. So from, and if F and G are homotopic, same.
You were saying that A and B are arbitrary
It's not.
not uniform.
No, nothing. First, big definition. So we are trying to do algebraic topology, but in an uncommutative setting is a sequence by the natural numbers of covariant functors from an admissible, very important category. C, which is of, so I cannot write mathematically, so I just write C and give an underline. This is category of C star algebra and star homomorphisms. It's a full subcategory of the category of C star algebras and star homomorphisms. 2, the category of abelian groups. So here the star is the general index. It's a function from C to abelian category, the category of abelian groups, such that one. One is homotopic invariant. So if two star homomorphisms are homotopic, which are from A to B, then so it implies star F equals star G, which is from star B. So these are functors. So applying them on a morphism makes sense. So these two morphisms from these abelian groups are equal. This is the homotopy equivalence.
So what is the mystical category?
Yeah.
Then okay. So for now it is a full subcategory of the category of six algebras and sarcomorphisms. Later we will see. So KK works for example, the first one A should be separable nuclear and B should be having a so B should be sigma nuclear. So you take for the if you fix the so KK is a bivariant functor. So there are two of them, H star and H upper star. So if you take the first one, fix A and then vary B, so you have C to be the all six algebras which are sigma nuclear. If you fix B and vary A, then you get another functor. There should you have, for C you should have A separable and nuclear, for example.
For the moment, it just means a full subcategory.
It's for the moment. For an arbitrary homology theory, it's some category. So H star comes equipped with C bar, C underline. If I
sorry, put your screen.
so AB are coming from C bar. So for six algebras inside C, if I have two homotopic morphisms, sarcomorphisms, then the induced value should be equal.
We are not in the dual category of this screen anymore.
Sorry.
We are not in the dual category of the screen.
Just like so the H star you just mean for all n.
Yes. So it's for a general n here. That was the first axiom, and the second is exactness. Here. Short exact sequence, which means A is a six algebra, B is a six algebra, this is surjective, this is a again another six algebra, such that the embedding is the kernel of this one. Essentially, A mod J is isomorphic to B. Then there is this sequence of maps. Okay, there is an index, but I am to keep it from H plus 1 to J. And long exact sequence. So H and R are covariant functors, so these three guys make sense. The map says how should we continue to the next one. This is the delta. So it's called a connecting map. Because this is a homology, this goes down. I'll say the result in homology in a moment. So, and then you should have here Hn minus 1, A, so on. So it goes up to H0. So for a short exact sequence, you get a long exact sequence with these maps. So this delta are natural transformations. That's it. So homology theory comes equipped with a domain C bar, underlying C, which satisfies the homotopic ingredients and the exactness. Axiom. another definition. Theory is additive.
Sorry, can I stop just to make sure I understand? So the natural transformations obviously don't depend upon the exact sequence. So you're asking for a natural transformation. I guess you've got a natural transformation for every n.
Yes.
A natural transformation for every n.
And the morphism, it should be natural with respect to morphism between short exact sequences. So if you have another one below it, 0, J prime, A prime, B prime, arrow, down arrow, then you should get a del bar prime and an arrow that this diagram computes.
Sure, yeah, it's a natural transformation, yeah. And then you're asking that for any exact sequence, the long sequence that's produced.
The letter diagram,
Exactly.
yeah.
Okay.
Additive is suppose you have the A is a direct sum of AIs for some indexing set I, then natural maps so for each I there is an inclusion of AI inside A. These are the induced maps. These give you ISO, which is this is called additive if given a direct sum, A creates with the direct sum. Similarly, I'll just say this in a remark. Homology theory is a sequence of upper indexed where n runs over n such that the homotopy invariance is same but both suggest the remnant. So you go this way. If you have f and g from A to B, then you go from H upper star B to H upper star A, and everything gets in the reverse direction because it's a cohomology theory. And cohomology theory is additive. If you have, so
There's a question.
the map from H star A.
Oh,
It is coming from H star I. Yes. It's the inclusion of AI to A that gets induced. Yeah. And a cohomology theory is additive. For example, so you have AI is included in A, that means for a cohomology theory, you get something like the projection onto the higher factor because it goes inside the reverse direction. You should have this be isomorphic to the product of H star AI. You just have to reverse the arrows. Okay. So this is the main theorem that summarizes. Sorry, for all the properties that they have. For each A, for and it is finitely additive. For each form a cohomology. This is countably additive. What periodicity code? T. Yes, what is called the substitution. So in the classical situation, you take a space X, make the cylinder, and quotient theta. So this is picture. So this is the cylinder. You pinch this point, you get the cone, and you again pinch this one. So this is the suspension. So for example, the suspension of the n-dimensional sphere is the n+1 dimensional sphere. Why this is the kind of definition? It just comes from usual isomorphism. So that is what periodicity. Can I erase this?
So, why is there an S2 and then S8?
That is suspend twice.
Suspend twice.
Ah, okay. Sure.
So
and for this theorem, is your notion of admissible say what you just said, like the phrase what it has to be?
so these are 1 and 2 does not hold for arbitrary C star algebra A and arbitrary C star algebra B. So to have 1, you need A to be separable and nuclear, and to have B, you need B to be sigma beta. And we'll see why when I almost sketch the proof of this theorem.
Wait, so sorry, so A was separable nuclear and B was sigma units.
Yeah.
Okay, right.
I have more periodicity here. This is 4. There exists pairing called Kasparov product. So if I write KK without an index, it just means KK is 0. Written as now the properties of this. Tensor D is covariant in B. What this means? So this will become here at the very last of the two talks. So covariant in A, B, contra variant in A. If you change this P via F and land inside F, X in KKAB, Y in KKEB, this implies, oops, don't think this should be X tensor over E upper star Y. So the lower star means push forward and upper star means pull it back. So it will be explained later on. I think yeah, it should be B. So X is in AB, push it through F, you land inside. So I have applied F on this variable. So I have land inside A comma E. Had Y in EB compose to get inside A comma B. And X was in AB, you pull Y through F and you get to B comma B and then take the product and you land inside AB. And the property says that this is what is equal. Five, six. Is associative, which means for all X in Y in A. You have so A, B, D, E, this means this is inside A, E, and then you up with Z, you get inside A, B. You do the same thing, but this one first. 7 for each A. Then 6 1 8. What's that? For all X in AAB, X in B with one A. So the product is unital.
So it wasn't question, an important question, but then, like, if you fix D, there should be some naturality between this. And if you fix D, then you've got a bifunctor on both sides, because then this should be some sort of a natural transformation. And this is what you're saying below.
So for the moment, this will be for star homomorphisms, but you'll see later on that they are actually Hamiltonian with respect to the Kasparov product itself. So these look like already a morphism set of some category.
Yeah.
So indeed, these are Hamiltonian with respect to the product.
Concern is basically like a monoidal structure and category of all KK groups of admissible cis-large.
The tensor product?
Yeah.
Yes, it is actually. So, and then if you have a triangular category with a tensor structure, you actually get a space, X, a commutative space, genuine space. That is called the Balmer spectrum.
I see.
Yeah. So there is immediate space behind the whole category. Yeah.
So what spectrum did you say was the?
So that is not have been computed. So Maya and some Clement, I have forgotten the surname. So they actually considered for a finite cyclic group. And I have no idea what the space look like.
But what did you say it was called? The Balmer
Spectrum, yes.
like BAL.
Is it possible to run the trivial case when AA comes out to be the trivial group, and then 1A is forced to be equal to the 0 in the group. So it's possible to end up using KKA consistent with single.
Yeah.
And how is this in cases characterized? Okay, because by analogy in topology, so when they define generalized homology, sometimes they say
You have the coefficient group.
but sometimes this is something about the normalization axiom. So you want your homology, for instance, at the point to be equal to, let's say, integers.
So yeah, it will turn out that for a point, so if you take both of them to the scalar C, you actually have Z.
You get Z.
KK C comma C is Z. So that is perhaps the minimalization. But since it depends on both, I don't know. So for example, if you take K3, and K3 we know does have 0. There are some spaces for which K3 is 0. And this is K3. K0, yeah. And then you apply suspension and get the K1. This is the compact on a separable space. I cannot say like math calculation. This came with a line induced by rank 1 projection. Isomorphic to, so is stable in both variables. That's it. So this age will let you apply KK without going into the details. So the remaining entirety of the talks will be to construct. So I didn't say what does KK actually, how is KK of A, B is constructed. So for that, we need a huge amount of luminaries. So that will be the entirety of the next talks.
First of all, this K is a compact operators.
On a separable basis, yeah.
And actually, do these properties define K?
Yes, and given, so if you fix, so for example, A to be separable and nuclear, all of the other homology, cohomology theories actually factor through KK. But the point is, if you do not demand A to B, so KK is defined in complete generality, except for B needs to be sigma unital for some reason. So you can take A to be anything. The point is, if you do not take it to be nuclear, there is a problem with the log exact sequence because KK is only half exact. To get the long exact sequence, you would need the completion of, in a sense, of KK to get the long exact sequence is E theory, Higgs and C theory. And that is universal always. So, but if you restrict to a separable and nuclear, KK is universal. And that characterizes KK, yeah.
So this means, so in fact, you can forget about these properties and just say it's monetary theories through
Exactly. Yeah. Yes. Yep. Yeah, that is what I said in this way. So this lets you compute, apply without going into the details. Yes. So the characterization was done by Kunz and Hickson. Kunz says more. So if you have these things and the two functors agree on spheres, then they would agree on a special class, which turns out to be the UCT class. Okay. Yeah. That's it. Now I'll give that to So I decided to start with input modules. I should sure all of you know stuff, but it just I like them so much, so just say it. So these arbitrary six algebra, Gilbert, the module is right B module with the map is the luminar product. Which is linear in the second variable and satisfies the following. So X, Y always come from E and B always come from the sister algebra. Sorry. So this one says it behaves well with respect to the module action. This is usual symmetry. And this is positivity and X non-zero implies this is strictly zero. So this is positivity inside the sister algorithm. There is a small lemma. So E is a free Hilbert B module, then set So take the inner product of E with respect to E. This goes inside B. Take the norm, land in C, and take the square root. Then normed vector space. What's that? The module action is submultiplicative and it satisfies Cauchy-Schwarz. It lets you define Hilbert B module. The Hilbert B module E, which is complete with respect to remark.
You remember that's for a jingle song.
The lemma lets you extend the inner product and the right mod structure on a free Hilbert module completion. We can always complete. This will be the as usual important. The completion doubles with the product being just multiplied star B. It will be the algebraic direct sum of complementary copies of B. Algebraic direct sum. So these are the sequences that eventually are zero. I.e. the set of all sequences that are zero eventually. Define inner product as you would in a direct sum and then complete. The module we get is a free analog. Is the analog of the free module in the algebraic case. So it is a special. Please note it. as A sub B, for B equal to the scalar if HB is just the 2 of M. So there is another example, but probably I wouldn't have time to say that. So you can ask, if we take B to be C0 of X, what are some natural examples of Hilbert modules? They can even be classified. This is the space of sections on a continuous field of Hilbert spaces. I think let's keep that in the for the end. Say something. Now that we know what a Hilbert model is, the admissible maps are as follows. So it's you want the P2 to be B modules. These are the admissible maps for the adjointables. With E1 equals E1 this term. For each T in this set is bounded bilinear. And so since T is bounded with respect to the norm, it lets you define the operator norm, and lemma says LBE, which is LBE comma E, is a
This fact that every adjointable T is automatically bounded and linear. I've only ever seen this in the context of Hilbert modules. It's like, but it seems like I've never seen it just for Hilbert spaces. You know, why doesn't one mention this very nice fact for just Hilbert spaces?
It goes in the other way. We first demand boundedness and then prove.
Yeah, usually we just find it every bounded one that's that adjoint.
Yeah, no, just a comment.
Yeah, so this is much cleaner. And you get linearity, not just linearity. So again, you want me to Hilbert B choose X in E2, Y in E1. I define an operator xy, which is defined as follows. You take z from E1, taking a product of y and z, y is from E1. It goes inside B, x is an element of E2, so it makes sense to multiply an element of B from the right to an element of E2. It turns out that theta belongs to the adjointables. In fact, the star is just a we define KBE to be the closed linear span of all these theta xy, where x is in E2, y is in E1, lemma A, B, E is here in delta equals. So if you take B to B C, K of A C of inverse C module, this is just a inverse space, is a compact operator. Compact. Ask for an explicit example. KB. So B is a Hilbert module over B itself. It turns out to be isomorphic to B via X Y star. It also gives you another sister algebra. So LBB makes sense, which we call the multiplier algebra. I'm sorry. This definition of multiplier, I could sleep in the night. Multiplier.
I agree.
Yeah, exactly. Yeah.
So that's a stupid question. That compacts your KB, that's a definition.
This is the definition.
So it's very good.
So we can spell of rank ones. And B is sitting inside this one via the isomorphism. Explicitly for B in B, MB of A, this is the operator, so this is just left multiplication by B. So this is one of the 1/2 of the centralizer approach. And this was the multiplier, yeah, that's it. So I'm now going toward the first substantial result of Kasparov. Hilbert B module. The street topology is the locally convex topology given by the family of seminorms indexed by X. So I'll just write what X is in a moment. The street topology on LBE.
What is the
Locally convex. So these are the seminorms. So if you take B to B C, E becomes a Hilbert space. This is a strong start topology. Hilbert A module. F is a Hilbert B module. A map from LAE to LBF is strictly continuous if it is continuous with respect to the switch on LLE and LP. Anything there? Just start algebra. Is a delivered E molecule. I is the star homomorphism from A to the jointables of E. The following are equivalent. There exists a projection P inside the jointables such that take the set of operators IA, apply it on E, so it's just a sub-module, and then close it. The thing is, it would be, so unlike the inverse base case, not all sub-modules are complemented. We demand that this sub-module be actually complemented, so it comes from a projection. There exists a strictly continuous extension I with the line unit from the multiplier to the joint. And so if phi bar exists, it is it's a star homomorphism, furthermore, it is strictly continuous. Mark. If one holds with E equal to the identity of E, then phi is called non-degenerate. Another lemma. Module I now is a star iso. Then the module is complemented with the projection in identity and the strict extension, which is phi bar, from the multiplier interjointables is So whenever again phi bar phi, the line beneath exists, it is unique. This is the first substantial result of Kasparov. Is the deliberate B module. This is star iso I from the multiplier of the compacts with the adjoint tables such that is identity it lets you identify the, as you would expect. So take B to be C is the compact product on the Hilbert space. The multiplier of the compact is having on the boundary of product. That's it. D F Hilbert B1. They are isomorphic if there exists a linear bijection I from E to F. That it is an isomer. Now the second most important result. So the stabilization theorem. Oops. Before that, sorry for that. Be the sister. Emitter. If there exists commutable approximatively the B module is commutably generated if there exists a commutable set inside T such that span of is density. That is just a natural generalization of finite generation in the algebraic case. To get a countable set, you take the subquantum generated by the countable set, it should be dense. Here comes the theorem that I was.
And so why don't you call it separable? Is there a reason?
It's less strong than separable. Separable implies stigma equal but not the other way around.
It's not free. Separability is free, right? You get an orthonormal basis.
Okay, okay.
Not all finitely generated projectives are free. Stabilization. E is countably generated, then but any finitely generated projective is a direct summary of a free, which exactly says the same thing, even identifies the direct summary. So this is the free analog. Already, E is countably generated and only if the compact is so to have the sister algebra B pass as a countably generated Hilbert module over itself, we would have the compact of the Hilbert module B, which is B, to be sigma neutral. That is why, so we'll see B will be treated as a countably generated Hilbert module over itself. And that is why we need the second variable in KK to be sigma neutral, just to pass B as a countably generated Hilbert module. Okay, so a remark. Take B to be unital. PSAE E is finitely generated as a finitely generated and projective as a DMOS the compacts are the full adjointables. Identity of E is Since the whole structure, the first part regarding the definition of Hilbert modules and stuff. Now some constructions. The first one is direct sum. Triumph given a finite collection of Hilbert B mod. Then the direct sum is the Hilbert B module with the following structures. So the module structure is as given as follows. And the inner product is I'm sorry, it didn't make sense. So this should be exact one. The component wise inner product. So why do we need the Kasparov stabilization? It will appear later on. So it gives you access to the proofs. Internal tensor product. It's a Hilbert B module. If is a Hilbert A module, and as the name suggests, I would want to tensor E with F, but E is a right B module, F is a right A module. To make sense of the even the algebraic tensor product, I would need a left B module structure on it, and this is defined by a morphism. So it's a star homomorphism. So that I induces a left B module structure on F. Its grid of X should be phi B on X. B is in B, X is in F. Then the internal tensor product ITP is a Hilbert A module written as E tensor over phi F with the following structure. So a simple tensor is written as E coming from E, there is a phi, the left module structure F. And the inner product is okay. So E and E prime are from E. So the inner product lands inside B. I will push it through phi. So that I will have F here. Push it through phi. It's an operator on F. So this is an element of F, and this inner product makes sense, and it goes inside A. So E tensor phi over E tensor F over phi becomes a Hilbert right Hilbert A module. That is the internal tensor product. I would say how it behaves with respect to morphisms. There exists a star homomorphism J from the adjointables on E to the adjointables on the tensor product. What's that? Take an adjointable, apply it on an element. It's just apply M on the first component and leave the remaining thing valid. And Jm is usually written as M tensor over phi with identity. That's it. Now the external tensor product. Is a Hilbert B module. F is a Hilbert C module. The external tensor product ETP is a Hilbert B tensor C, where this tensor product is the minimal one. Module written as E tensor with the hat F with the structures given as follows. an element is a simple tensor is written as again with a tensor with a hat. So this is an element of the minimal tensor product, and you just multiply component wise. Let me write x1 y1, which is so x is in E, x1 is in E, so this is in D, y is in F, y1 is in F, so this is in C, and this is in D tensor C. And this is the star homomorphism, injective, which is from LVE to with LCF to L tensor C of E tensor F. Take two operators M and N, apply it on a simple tensor, and it would be MX tensor NY, and this is as you would expect written as. Furthermore, J maps the compact times the compact C inside the compacts. These constructions will be heavily used in the entire process of getting the Kasparov product. It's a small lemma. Yes, with the unital star homomorphism to the multiplier on B, it is lambda B. Then so it should be mathematical H with. This is the separable Hilbert space. So we call that internal tensor product requires. So you have a module over here, you have a module over here, and connect the two modules via morphism. Then the tensor product of this module with respect to this module makes sense. The module over C is H, the module over D is B itself, and I tensor with S. I get something, and this is the free B module. Another lemma. This is star. So one can ask what is the bounded adjointables of the free module. It is so in this case the compact on H. I use these isomorphisms, so which also mapping KB of HB onto that's it. So I use this isomorphism to get an explicit description of the adjointables on the free module B. It is just the multiplier of this one. A few definitions remain to finally go on to defining the Kasparov modules.
And so behind the leaf, it's a B, right?
Yes.
So in this lemma, we have an isomorphism between compact, we have compacts, tensor compacts on B, you could think of it this way, and then compacts on the tensor product. But here you have just an inclusion. So are there any other circumstances when you actually get an isomorphism like you do in the lemma?
So it's sorry, it's on yeah. This no, so I'm sorry, this is injective. So the isomorphism is for in general it's not true. So if you take B to B C, then it's
So this is something special about B being complex number.
yeah.
Okay.
Aggregate sister algebra. Is sister algebra B with an order of star homomorphism beta B. Right here. So this is the grading. So B gets decomposed into the eigenspaces of B beta. So given two braided sister algebras are graded homomorphism star homomorphism phi from A to B such that it is compatible with the grading. This is phi, this is beta A, this is phi, this is beta B, and this commutes.
Sorry for my question. It's a Z2 gradient.
Z2 gradient.
Okay. Could I say a super?
Yeah. Commutator. So for elements inside a graded sister algebra, the graded commutator is mod A times mod B, BA, where mod A, mod B is a homogeneous degree of A. B also the degree of, so they are homogeneous degree. Now that I have graded sister algebra, I can define what a graded Hilbert model will be. Then I'll be true. Graded Hilbert module over graded sister algebra B is a Hilbert B module E with a bijection SE which goes from E to E, such that so it should be well with respect to the Hilbert module. So B module structure, it should be, it is a grading, so it should be order 2, and it should behave with respect to the inner order. So this is another definition. So we need, so see, we define countably generated Hilbert modules. This is a countably generated graded Hilbert module, countably generated graded Hilbert B module is a Hilbert B module such that module which is generated as an B module. So the underlying B module is just countably generated. There are some examples. B with it is called the trivial grading. Similarly, E with AC to be or graded E defined to be so this is a grading on the adjointables to be T mapping to conjugation by the grading. This is called the induced grading. It takes compacts onto compacts, hence induces a grading on the compact. So we have defined countably generated graded Hilbert module. To have a graded version of the stabilization theorem, we should have also a graded version of the pre-module HB, which is defined as follows. So B graded system algebra S is from HB to HB defined as follows. We apply the grading of B component wise. Graded version of the free module, the two copies of HB with grading S direction minus S. So S acts on the first component as S and on the second component as minus. So you have minus before each component. And with this one, the stabilization theorem goes to part B. E countably generated graded and this ends the preliminary part. Now we will define the KKs.
My question again, if you have an even part, if you have a graded system algebra and graded Hilbert bimodule, then if you will take the even parts, it will be again pair of system algebra and Hilbert bimodule. Right? But you couldn't define the Hilbert bimodule structure on the whole bimodule for even part, right? Because your inner product will take values in all parts sometime, right?
Yes, yeah. You take E0 and E1, you land inside the B1.
Yes.
Yeah.
Can I ask this stupid question? So if you have a gradient, how do you define the even and the odd parts?
So I meant 1 and -1.
So how do you, the stupid question is how you do like define this 1 minus 1?
So B upper 0 is all those B and then
Okay.
and this should be I should say yeah, so the 1 you take minus.
Yeah. Got it. Thanks.
Algebras not having any non-trivial integratives, right?
You?
There are algebras which do not have any non-trivial integratives. For example, take the odd-dimensional algebra.
Yeah.
And there are probably also the here I could be mistaken, but I've read somewhere that the algebra, it's a continuous function in Polish space.
Yeah.
The complex space also doesn't have anything. So if one considers the space, the set of all possible gradients on a system algebra, the information from this.
No, so the way would be you just multiply the second Clifford algebra C2 to get theoretically they are not so distinguishable, so it would be okay. If you don't have a gradient, you just take 2 copies of it.
Well, I was asking if one can quantify, for instance, distinguish algebras which have a lot of gradients.
Yeah, so it would be like classifying all Z2 actions on a sister algebra. It's just a Z2 action.
Okay.
So I don't know so how to classify it. So you can like classifying them should mean up to something outer equivalence, for example, but I have no idea how to classify them.
Probably could be reduced to some non-linear equation for derivations, and then it's quite wild.
Derivation.
Yeah. You can think about Z2 gradient as a derivation, which is a specific property.
Yeah.
But this property is non-linear usually, and it's only characteristic to it. Nice. But it's kind of usually quite wide problem, even for something higher dimensional. I was plugging on. I don't know. All right.
Sister algebras would be graded from now on. And if I denote something like A1, A2, so the first variable of the would be KK group, they are assumed to be from the, sorry, it should be the second one. We just assume all of them are graded and sequence. Kasparov A, B module. Is a triple. Again, it is written as material E, which I cannot write. Again, this is a really oops, sorry, it's written an hour.
Should we actually move?
Yeah,
Probably should to if people move from her. So maybe after the definition, or it's long.
it's long, yeah.
Yeah, maybe you should move that.
Just move, yeah.
Natural.
E is a countably generated right Hilbert graded B module phi is a graded homomorphism from this graded sister algebra to this graded sister algebra. So this has the induced grading. If is an element of degree 1 in the joint tables such that the graded commutator of f with each phi a is infinitesimally small. So these are the small parts with a is in a. So this says that f almost commutes with the left a action, which is given by phi. This seem bigger, yeah. So f squares up to identity, almost squares up to identity. Again, a is in a, and f is self-adjoint, almost self-adjoint. Yeah. So bold E of A comma B is the set of all Kasparov AB modules. Okay. So now the set of all. Yeah, Jyotishman taught me that. Direct sums. So these belong to, take n many of them, then so this is the following triple. So this is the the direct sum of Hilbert modules. I will say what these are. Before that, where phi through this is from A to I is from 1 to n is defined as A going to phi 1 A direct sum. So this is the one you would expect. So here, so it acts the diagonally. So here for this is the direct sum. Now the pullback. You have a Kasparov module, a Kasparov AV module, and you have a star homomorphism from another sister algebra C to A. Then the triple E, first you go through psi to A and then apply phi and let the other remain as they are, is a Kasparov CB module which is called the pullback, written as psi upper star of. So it's as you would expect. So think of this as the Hom set of all the morphisms from A to B. You would have a morphism here that goes into A. You just pull it back and then get something on the thing that you started with C. This is the called the pullback is upper star. Now the internal tensor product, again it's E phi F in and so I have pulled back through here. Now I would go this way. Psi is a star homo. Then so for the internal tensor product, you call that we have a, so there is a connecting homomorphism. There was a module over B and there was a module over C. The module over B is already given, it is E, and I take the module over C to be C itself. So this makes sense. I also had a morphism between the adjointables. So if you have a morphism, an adjointable on this module over B, then I could have identity on the second component, and then that will be a morphism on the tensor product, internal tensor product E tensor C. So this is and so this lands on, and it is written as psi lower star of the class. So a Kasparov AB module is a triple where so you have A, B. I view it as, so you have A over here and B over here. So this is the module. A acts on the B module E, and you have, so the action is via phi. And this is the pseudo differential operator that is being hidden here. So F is the operator on E, which almost commutes with the A action. It is square, it squares to identity, almost squares to identity, and it is almost self-adjoint. So yeah, and we have direct sum, pullback, internal tensor product, and now the external tensor product.
So that's where this definition comes from, pseudo differential.
Yeah, yeah.
Because it seems right. Yeah.
So I'll just explain that in a moment. Yeah.
So we're considering 5A. Yeah, and what if you describe it as and B, but then of course you don't just want the Weimann, but you want the action basically on the right side to also act like a
So it is, F is itself an operator. So you just compose the operator. Yeah.
It's not just the Weimann, it's that the action on the other side is actually acting in a way.
Yeah. Yeah. Yeah, you don't need the, then you don't need this too. Yeah, it's just F's all up. Surely it's infinitesimally squares up to identity, and then it's infinitesimally self-adjoint. Yeah, and that is where the idea stems. So if you can, yeah. So this is the measure zero in some sense, and then the LP lies inside this measure. So this is okay. So yeah, these are the small stuff. Yeah. The external tensor product. So you have in I do.
What a speaker. Yes,
See graded sister algebra. Oh, by the way, so here I am tensoring with respect to C. In the definition, I demanded that all the modules be countably generated. So I want to see C as a countably generated Hilbert module, which means that I should have C to be sigma unital because it is the compact of itself. And that is why sigma neutrality is required for all these algebras. It's countably generated. So by stabilization theorem, if you add the free module HB, you would get HB. Yeah, C star algebra, then E is the B module, C is the C module. It's phi tensor identity. So this is the image of the canonical morphism J, which I defined. This is in E A tensor C, B tensor C, and it is written as tau C of, yeah, that's the external tensor product. Okay. And so I just refrain from writing it. So if you have Kasparov AB modules, an isomorphism should be an isomorphism at this level E, which intertwines with phi and which intertwines well with F. It just commute the diagram, all the square diagrams commute. Here, so AC tensor beta C, yes. Okay. So our lemma says, if you have, so I'll just, it's too much to write the one, so I'll just bear with me for my math class. Then and let 0 denote the trivial class, then so we indeed have a product or an additive operation on the set of all Kasparov AB modules. So recall IB, it was, and there was also the evaluation at T, which is a surjection from IB to B. So observe that E is in A, comma. So recall the definition of a homotopy. It was a star homomorphism from A to IB. If you think of this as some sort of morphism set, a homotopy should be a morphism from A to IB. So if I take such a morphism AI, then and I push it through phi t, so that pi t. So here is E. You push it through pi t, you land over B. It's in. So it's the internal tensor product, right? This one. Definition. So this is the counterpart of applying pi t. So a homotopy was, so you pi 0 H, it should be the first star homomorphism, and then pi 1 H was the second homomorphism. So it would be precisely the same. Homotopic if there exists G in such that pi 0 star of G is isomorphic to E, pi 1 star G is isomorphic to F. and we write, so you can reach from E to F if there exists. It would not be a good idea to write it here. So we write if there exists a finite set such that E1 is E, En is F, Ei is homotopic to Ei plus 1, I running from 1 through n minus 1. So you have a chain of homotopies that connects E and F. Okay. One more definition, then can define what the Kasparov groups are. Degenerate if B is unital, we can ignore okay. A degenerate Kasparov AB module is a the name suggests what degenerate should be. It's in does that. Okay. Okay, so this we already could have defined the Kasparov group as E of A comma B. So okay, I didn't say it as a fact. It would come just after the definition. So the thing that connects E and F is the what is this called? It's a seam, right? So yeah, it is an equivalence relation. So if you quotient E of A comma B with respect to the equivalence relation, you get KK of AB, but it wouldn't be sufficient to just have that definition because the product is not naturally defined on the KKB. The product would be defined on the thing I'm going to write now. It's easier to define on it and then prove that the two definitions coincide. Yeah, yeah. Because so suppose you have 3 E, F, and something else E1 probably. Then, so the usual idea of proving the third condition, which is the transitivity, is to partition the square diagram with a triangle. That is very difficult here. That works if you take that. If that's, yep. No. So it is not defined in this way. It is defined in the following way. This is the standard idea. So if you see the definition of K as follows, so you add free stuff and then you would get isomorphism. So the first idea is to define direct sum, then unitary equivalence, and then a trivial stuff which you add to the elements of K and then get iso. So I have defined the trivial stuff. This is the degenerate ones. I have defined what an isomorphism is. So this is the that version of homotopy which would enable you to proceed through as you define in K homology. This is the one. R operator homotopic. If there exists a countably generated graded Hilbert module E, phi a graded homomorphism and E is a B module, yeah. And non-continuous path Ft inside the jointables such that the triple is in AB. Observe that here it is, so all these triples are indexed by T. That means to have a homotopy between E and F, you vary everything, the module, the left A module structure and the operator F. Here we only demand that only the freedom operator varies such that it is in AB for each T and F0 is isomorphic to E1. I have is E1. You get through E1 to E2 via a path of freedom Kasparov AB modules, but where only the freedom operator varies, the first two components doesn't vary at all. It sounds strange. It seems to be a very weaker homotopy relation, but they give the same answer if A is supposed to be separable. And that was Kasparov's, one of the main results. So we write with approx if, so when there exist degenerates this is the one I was talking about. So you define direct sum, you define unitary equivalent, and then you define some trivial modules or trivial elements of the would be K or KK, whatever the group is. And then the idea is to have the equivalence relation so that you take two modules, U1 and E2 should be equivalent if you add trivial stuff, and then the result becomes isomorphic. It is just exactly the same philosophy. So this is how Atiyah proceeded with K theory, with the K homology he proposed, but he couldn't figure out what the homotopy relation should be, and this is by Kasparov. And that is why Kasparov comes, such that E1 direct sum F1 is isomorphic to it is an equivalence relation. So KK AB is EAB with respect to the equivalence relation I just erased, and the class of E is written as square bracket E, and here with a hat on the second leg. The Kasparov defined it in a slightly different way. This definition is by Skandalis. And the class is written as curly brackets E. Lemma says this way here. So it is homotopic with respect to the operator homotopy, gives you that it is homotopic with respect to usual homotopy, which means there exists a map from hat KK to ordinary KK, which sends in both cases. So it is, so there is all those, you would need to prove that if I choose the different representative, this would give the same class inside here, and it is also the same definition. No, so it is just a map for now because there is no structure yet. I am just now defining the addition, and 0, sorry, are identity respectively. Now I can state the first theorem. abelian groups, and mu is a surjective group homomorphism. Yeah. Yeah. It's just, it sends the class of E at the.
Yeah, well, yeah, it's somehow.
Yeah.
Yeah, but does it say some functor on the figures before?
So both of them are defined on the same category, but the equivalence relations are different.
Yeah. You know.
Okay. And I just state it briefly. It's a star homomorphism. It's a graded star homomorphism. Then oops. Yeah. Okay. So if you fix C, then in the usual case, suppose it is harm, and you fix the second leg, it should be a contravariant functor. In this case, it is also a contravariant functor. So it is at the both of them. So I just put the is in the both of the groups becomes functorial contravariant functor with respect to the fixed second component, and it sends a class of E respectively the curly bracket to the class of it was the pullback. And if you have it also holds for the curly bracket. If you have B to C star homo, then if lower star is from K A B to AC, you take the class of E, it goes on to this is the internal tensor product. So that is what is meant. So for the first properties, I need kk star of the first variable to be a covariant functor, which is, so I have obtained an abelian group, and this says that if I fix the first variable, I indeed have a covariant functor. The second one says that it should be a contravariant functor with respect to the second variable, and this says that I indeed have a contravariant functor. So these are the functorialities. I still have a lot way to go. Yeah. Okay. No. So this has been used. I have erased the definition. Oh, is there? Yeah. U1 is homotopic to. I'm sorry. Okay. That's a mistake. It should not be. It should be operator homotopic. I'm sorry. Yeah, I'm sorry. Yep. I'm sorry. That's a mistake. Both of them are operator homotopic. Yeah. Thank you. Okay. This is functoriality. This would be needed later on, so I'll just straight it. A, B, D are sister algebras. There exist group homomorphisms. Tau D. So I have used pullback internal tensor product. The external tensor product remains. This is the one. So I'll again put a bracket A, B, 2 KK of A tensor D, B tensor D, which sends class of E to the class of the external tensor product of E. That's it. It's again second bracket, the curly bracket works. Oops. Yeah. So maybe a sketch of this one. The idea is that if E belongs to, it can be represented by where, so I need to specify the grading on H direct sum H. So H is a Hilbert space obviously because I have taken the sister algebra to be C. So H direct sum H is graded by C obviously has the trivial grading. Is graded by psi chi go to psi minus chi. Phi is the unique unital star homomorphism from C to the boundary operators on H tensor H. And you can choose S and T in the boundary operators of H, which are unitary modulo compacts. Oops. Identity. T star identity mod compact and again modulo KH, which means so T is unitary, S is a unitary. So in particular, it is it's a inside. So it's a unitary in LH quotiented by KH, hence invertible, which means that S and T are both freedom operators because it's invertible in the Kalkin algebra. So index of T makes sense. I define to be take E in this is called the standard form of E. So E, take E and then reduce to the standard form and then send it to index of S or S or T. It doesn't matter really, index of T. Yeah. And this is an isomorphism. So the first big step, KK hat of C comma C. So when we say that KK hat and KK are the same for the first variable separable, then it would mean that KK of C comma C is also Z. I think I'll just keep the homotopy invariance part because it requires some more stuff. So that would, so KK, it's almost from the definition that both of the bifunctors are homotopy invariant, which means you have homotopies and it would induce the same map, so that I have the almost the first two part of this big theorem. Recall that to have a homology or cohomology theory, I need the exactness axiom. That would come much later on because that would require something entirely different. Okay. Yes. Yep. Shall we take a break? It's 5. And then, yeah. Okay. So now we move on to define the Kasparov product. So what we should be doing is that we have something here and something, an AB module and a BC module. We would like to have something E12 in EC. So it should be the first two candidates are almost there. So phi is E1, phi 1, F1. It is E2, phi 2, F2. So phi 2 is from B to LC of E2. So that E2 is a left B module and E1 is a right B module. So it would make sense to consider the internal tensor product. This makes sense? Natural enough for the candidate, first candidate of E1, but for something like a product E1 dot E2. So this would be from A. So again, this makes sense. The problem is what should be this, and that is also evident from the theory of connections. So for example, if you have, suppose on E and on F, or these are vector bundles, so on E prime, then is not an option on, rather the coproduct on the Lie algebra lets you identify what should be this. This should be the problem is, it was long ago observed by Atiyah and Singer themselves that, so we are taking degree 0 differential operator, pseudo differential operators throughout for the classical example. This would in general not be a even a pseudo differential operator, let alone the degree. This would not be a pseudo differential operator. This would not be pseudo local. For connections, these are local, but for arbitrary pseudo differential operator, these are not what is called a pseudo local. But what they were able to prove is that there are operators M and N which are positive, and M and N add up to 1, such that F1 tensor 1, there should be a square root. This indeed is a degree 0 pseudo differential operator for the classical case. At least they managed to prove abstractly. Then, so something like this already existed in the early 70s. Then Kasparov came and proved that these guys exist for arbitrary sister algebras, and that is what the technical theorem says. So I'll just state the technical theorem for Hilbert modules. It's a countably generated, graded Hilbert module over B, and B is sigma unital, as we have already assumed. A1, A2 are sigma unital subalgebras, sister subalgebras of LBE. F is a separable subspace closed. It's a linear subspace, so closed. Furthermore, assume so I write the induced grading on LBE by beta E. It takes AI inside AI, I from 1, 2. If you multiply A1 and A2, it becomes small and it derives well. Okay, I have used all of the, sorry, this is A1. Then there exists operators on E of degree 0, such that Mn are positive as you would want. Mn adds up to 1. M takes A1 to the small part, N takes A2 again to the small part, and again small. So the entire proof of the existence of the Kasparov product is by ingenious choice of all the ingredients of this theorem. So you choose A1, A2, F such that these three conditions hold, and then you would have the partition of unity M and N, which would allow you to write this expression. So this is it should be again so in the classical case it is almost clear what should M and N be. It should be the norm of this one, square root sum, and then divide, because it goes up to something higher, you just divide by the norm, you should get something less than norm 1, which should be 0 in this case. So that is the idea. But in the non-commutative case, you cannot make sense of this, as would be becoming clear now. Okay, so before that I would define That's it. This is the technical theorem, and the proof is even technical. This the theorem itself called technical. Yeah. Okay. So now the setup. So E1 is a Hilbert B module. E2 Hilbert C module. Let's just write F instead of phi2. Phi2 is hectic. A star homomorphism, so that I can form the internal tensor product E1 tensor E2 over F, and I write it as E1 E sub 1 2. It has grading SE1 on this one and SE2 on this two, the tensor product of the two. For each x in E1, Tx is in LC E2 so takes E2 from this and puts x before E2. It's called a what's it called? I forgotten what's it called. Yeah. And it's adjointable with an explicit adjoint. The meaning of why we need something like this, it will be clear in a moment. Let should be LC E2 direct sum let. So I have so far taken I have omitted entirety of the first phi1 and f1. I have not taken f2. So here comes f2. And f in LC of E1 2 is called an F2 connection for E1 when this graded commutator is small. So this looks weird enough, but it will be clear in a moment. Before that, yeah, this one.
Because two doesn't depend on this tensor product. One tensor.
Yes, yes, yes.
They only have one copy of one.
It doesn't have a problem with. That would be, yes, very good. Yeah, that's a nice point. Yep. So in a moment, so F will be the freedom operator in the Kasparov module. So F would be having degree 1. So I'll just write, so this, since this is a graded commutator, I'll just write what it means to have a graded commutator for a degree 1 F and a degree 1 F2. So this is the following minus FTS E1 X. This should be in and F2 Px star minus this is the graded commutator. So let me now say why it works. I'm sorry, the X should be here. Yeah. As Andre said, we would like to have some combination of this plus one tensor F2, right? So this is the pseudo-differential operator. But F2 is a C-linear, right C-linear operator on E2, and we don't know. So these tensor products, or where is it? So yeah, this is over B, right? So to make sense of this, we would be needing F2 to be left B linear, which means it commutes with the phi 2 action. But we know it doesn't, because the commutator is a compact. So let me now write. So suppose we have something, some F here as a replacement. I would like that to be one tensor E2, which is it should be on E2. This should be X on 2, right? So one tensor F, I write it abstractly as F. It would act on a simple tensor as, like this. So what is this? This is Tx E2, right? And this is Tx of F2 of E2. So to have something meaningful like one tensor F2, we should have this thing vanish. But to demand it that it vanishes is too much. So we require it to be small. And this is the one. Ftx Tx F2. This is small enough. So the first condition says that my F is a suitable replacement of one tensor F2. And the second condition would be, let me erase this one. This condition is for F2 and F1 having degree 1. There is no, so it's a graded commutator, right? Yeah. Everything is graded commutator. Yeah. So we would be exclusively dealing with Fs which have degree 1. This condition in is a compact is equivalent to these two conditions, given that F and F2 have degree 1.
Okay, right. And by the way, there should be KFC, not KFC.
Oh, so I'm sorry. Yeah.
Right. Then so if once we know this.
So we would like to have the pseudo-differential operator on the Kasparov product on the product. So A comma C would be something like this, right? As I mentioned last year, so it would be the differential operator tensor 1 with the differential operator 1 tensor the differential operator. But it doesn't make sense because F2 is not left B linear. The commutator is a compact. So we have to choose a suitable replacement of this operator. This doesn't cause any problem in the classical case. So we have to choose a suitable replacement of this operator. So let us see what a suitable replacement is. Suppose F is a suitable replacement, which means that on a simple tensor, it acts like X tensor F2. If you write this down, so X tensor E2 is Tx of E2. And this one is Tx of F2A2. This should be equal, which means that the difference should be 0. But demanding it to be 0 is too much, so we demand that it be small, and this is the first condition. It's precisely the same term. And now the second term. I should write F, the replacement, or just F2 probably. The adjoint turns out to be like this. Should be, it's a little computation. So you see, F2 is not, so X and E1 are both from E1. So it is, it is inside B, and the difference we should be demanding that it should be small enough, and this is precisely left B to linearity of F2. So we demand that F2 be almost bilinear, and it's a good replacement of, and F be a good replacement of 1 tensor F2. So that is what a connection is. And we need to say if it exists, it indeed does. If E1 is countably generated, is of degree 1, and if the connection exists. There exists an F2 connection for E1. So all these requirements are satisfied by a Kasparov triple. The first one is countably generated. The second, the operator on the second module is of degree 1, and the commutator with, so this would be phi 2 in a moment. So F2 comma phi 2b is in fact compact, which means that for like 2 Kasparov modules, an F2 connections always exist, and that would be the replacement for 1 tensor F. So now that we know connections exist, let us take two Kasparov modules from so a Kasparov AB module and a Kasparov BC module. Right. As usual. So this should be phi1 tensor phi2 from A to LC of E12 triple E12 phi1 tilde F in E of A comma C is called Kasparov product. If F is an F2 connection for E1 and another condition. So this one says that E is needed for the existence, and this one should be uniqueness. So we would want the first part of the F to be F1 tensor identity, something like that. So this almost says that with F it's positive but mod compact. So Kasparov product is consists of the triple E12 phi1 tensor identity and connection. Where is the theorem? A is separable. I am not writing out the triple thing, just save time. So E1 is a triple which is in AB, E2 in BC. There exists Kasparov product E12 in C, which is unique up to this is where the operator homotopy comes in. Homotopic. So this is why we need operator homotopy. So it is just a single step to reduce, to get descend down to the group level KKAB SE. You want the class of, so the product is again, you have to prove that if you take the class of E1 and you take the class of E2 and then consider the class of E12, it genuinely gives you a class, which means that choosing different representatives doesn't matter, and that is the Kasparov product. But with respect to the operator homotopy, so we would be landing inside kk hat of AB. And it is a wonderful theorem that if A is separable, then kk hat AB is kk AB. So you indeed get to kk AB. So the theorem goes on, the proof goes on as follows. So given this data, you choose very judiciously your A1, A2, and AF in the technical theorem, and you get M and N. The previous lemma, where is it? So the proposition guarantees you with a connection so that this condition, this thing makes sense. Suppose I write G for the connection that is guaranteed by the proposition. You have M, take the square root here. You have N, take the square root here, and this is your F. So this is the Kasparov, the pseudo differential operator. And this is unique up to operator homotopy. Yeah, we're almost done. That's it. It gives you the product. So I have. So I am not ticking it yet. So it's half tick. It's half tick. What periodicity is left? This is done. So the product is, again, it requires a theorem, which I would state in a moment. G is the connection, F2 connection that is guaranteed by. So you want to, in the definition of Kasparov product, you require a F to be an F2 connection for U1, right? So this whole thing would be a connection, but the thing is so set up that you indeed get a connection for. You get a connection. You apply the proposition in that scenario, you get a connection, right? That is I write. So that connection is G. So that is a replacement for one tensor F2. So you take this linear combination, it gives you the pseudo differential operator. G2 is the replacement for one tensor F2 because it doesn't make sense. They are degree 1 differential operators, right? So yeah, if you take the bounded transform, you would get a homology class, and it is called a connection because there is a unbounded picture too by Baj and Joule, and that is actually behave like a connection. So there is all these stuffs are unbounded, so they have precise domain. For unbounded stuff, you don't have to worry about these things. Exactly. And that is where the square rooting things comes in. And this is precisely the normalization. It's a partition of unity. And for the unbounded picture, you don't need to. For the unbounded picture, you don't need to have these things. Easier to, yeah. But it doesn't give you really necessarily more information because you just get the statement that the product exists. But to compute it explicitly, unbounded operators are hard to deal with. Yeah.
This is condition 2 here. I'm not very. What's this saying? How is this a unique?
So I have skipped a lemma which says that if you have like two Kasparov modules E phi F1 and E phi F2 such that replace here F1 and F2 and take this expression which is positive mod compact, then their operator homotopic. I have skipped this. So this comes from Kohn and Skandalis. So they proved that that lemma comes first. So if the difference is positive modulo compacts, then they are operator homotopic. There has to be operator homotopic, and that is what is giving you the uniqueness. What do I plan to do? Yeah, okay. So I've defined the product. It is associative. And that requires a huge preparation, but we'll skip it. Yeah. So I have defined the operator. Everything holds in here. So contravariant covariant now is clear. So these are contravariant covariant functors. So if you right, so I should write just write it as a theorem. There exists dot from this is bilinear in both variables, such that one, if you have and G from C2, these are graded homomorphisms. So F is pulling back. So X is in KKAB, Y is in KKBC. So F pulls back. So X goes on to KKA1B, and then Y coupling with taking the product with Y makes sense, and I land inside KK1 of KK of A1 comma B, and X5 makes sense. Is just again pull it back through F. So this is the contravariant part, and X times G star Y is these two are the covariant and contravariant, and these hold. Okay. Let so C is a Hilbert module over itself. Take the unique unital star homomorphism from C to C, and the operator is 0. So this is called a canonical class. For any C star algebra A, for A, let mu A, sorry, take 1A to be. So recall the external tensor product, it would give you C tensor A, comma C tensor A. That means A E of A, comma A. So it lands inside E of A, comma A. And the class of let me not call that. So let me write it as UA. UA, yeah. Then 1A is the class of UA. So which gives you the unitality. Yeah. Now the theorem, A is separable, then it doesn't say that KK hat AB and KK AB is isomorphism. It gives you the precise map, which was the map initially defined. Is an. So you get everything down to KK, not just KK hat. There's associativity. Yeah, we're almost done. I would now state something which would be taken up by Sophie in great detail. So D, E are C-star algebras. Assume there exists alpha in and beta in such that so alpha is D comma E, beta is E comma D, so tensor over E makes sense. This I demand and it lands inside D comma D. Beta is E comma D, so tensor over D makes sense. I have alpha, it lands inside. Then okay, then next board. Now is the magic of Kasparov product. So you see alpha and beta are inverses of each other up to the Kasparov product. That gives you entire a series of entire isomorphisms. Then for any A, B, there exists so think of this as the Hom set. You have A comma B tensor D, and you have alpha from D to E. So this would be A comma B to B tensor E. And the inverse is natural enough. So it's, yeah, it's an isomorphism. It's the inverse. And D tensor A comma B to KK E tensor A comma B with the inverse alpha tensor. When such alpha beta exists, we call that D and E are K equivalent. Now we'll see some examples of that would give me how do K equivalent. The sister algebras D and E are called K equivalent. So producing K equivalents gives you 3 and 5. Yeah, this one. So recall suspension was tensoring with C0R. So double suspension means tensoring with C0R twice, which means tensoring with C0 of R2. So what we would need, so this one. So this is C0 of R2 tensor B. So D would be C0 of R2, right? And E should be C. So we would be producing an equivalence between C0 R2 and C. And that is precisely this. So beta is the class of, so beta is represented by the class E phi f in E of somewhere C comma C0 R2, where E is just 2 copies of and it is graded as follows. So F1, F2 goes to phi is the again unique unital star unique unital star homomorphism from C to the adjointables, and F is as it's P star xi is I. P is from minus S plus IT xi ST. This gives you beta. So this is the K theory class inside here. This is the bot element beta. And I have to produce a K homology class for which we would be needing Hilbert spaces. And the most natural thing to, oops, sorry. To be the class of H phi D, where L2 of R2 directs some L2 of R2. It's graded by the same techniques. Psi chi goes to psi comma minus chi. Pi is the action by multiplication by a C0 function, and D is where T is defined using Fourier. Then beta tensor C0 R2 alpha is 1. So beta was in C comma C0 R2, alpha is in C0 R2 comma C. So this tensor product should be in C comma C, which means that choosing a standard representative of this fellow and computing the index, you get 1. And the other direction is automatic from one of Atiyah's trick. Applying this equivalence with to the theorem, we get bot periodicity, and that is 3. The Fourier transform. One more thing remains, the short 2 things remain. So it will be done in a moment. Yeah. So first 2 facts. If phi is a graded homo, then B phi 0 is an element. Okay, so this is in E of AB. So B is a B module, phi is going to the compact, so the adjointables, and 0. This gives you a canonical class. This is the homomorphism class associated to a homomorphism. More generally, if you have phi from to the stable B, this is K, then is a graded homomorphism. Then again, so it will take HB phi. Recall that B tensor K is the compact of this fellow, and 0 you get now. For the stability, again observe that we have to produce an equivalence between C and K of H and apply the abstract duality theorem, this one. So I'll just produce the elements. Okay, maybe here. So I should keep that one to have the isomorphism. I'm erasing this one. What is alpha? Okay. So take A to be KH, B to be C, so that we have the identity from KH to KH, right? Taking A to be KH, B to be C in the second condition, which means that I get an element alpha in KK of KH, comma C. Let H, this is the induced by rank 1 projection. It is known that okay, I just skip it and say what the beta is. Yeah, take beta to be, so the identity is in C comma C, and if you push it forward through this morphism, you get C comma KH. So and these two are indeed inverses of each other. So you get stability. Almost all of them are done. The first one I half tick. So for that we need a concept. Oh, okay. So there is a comment finally. So I should write it here. So last year Bishan's talk, see, he proved Bott periodicity using the Topli's extension, right? So you had this short exact sequence. So you get two morphisms Q from T to C. This is composing with the evaluation at 1, and J is from, it is the unital embedding. So the entire thing goes into proving that these two are K equivalences in the sense of this. So that there is a step where you multiply arbitrary cis algebras A and get isomorphisms between A tensor T and A itself. That is the proof of Bott periodicity. So you are actually providing K equivalences. Yeah. Yes. Okay. Maybe erase this one. The last step. An extension B is semi-split if there exists a completely positive section S of, okay, let this be J and this be Q, section S of Q. Completely positive means you go to the all the matricial level and you get positivity for all n. Yeah. For example, if you have A to be nuclear, so A nuclear implies all extensions are semi-split. The theorem is semi-split, then I think I should write it A mod J because B will be the second variable. Then okay, for any D. Yeah, I have space enough. A K D A comma J. This is KK1 D comma this is A mod J. Yeah, sixth term. Yeah, because we now have bot periodicity. Yep. So these are the connecting maps. And this is exact. And there is this other one for this variable too, and that goes in a opposite direction. I'm not writing it. So yes, I think that's all. I have some references which I would just write down here. Okay, so it is fun to take them. Vincent Thompson, chapter 1-2. Blackadder, chapter 8. There is a note by Skandalis on his website. It's called Kasparov's bivariant theory. Cone. The book, and it's an appendix to chapter 4. Appendix A. Dixon. The note is called A Primer on KK Theory. And obviously, Kasparov paper is called operator K functor. Operator. Yeah, that's it.